At this lesson, we're going to look at predicting redox reactions and whether or not they are spontaneous. So we've looked at some half reactions, for instance the silver half reaction where silver ions go to silver, and that same reaction can be written exactly the opposite. As you know, some reactions are reversible. So the silver ions going to silver flipped around becomes silver going to silver ions plus an electron. So the opposite reaction to a reduction reaction is the oxidation reaction. Where these are often shown using that equilibrium notation we learned about earlier in the course with the double-headed arrow. So we can look at these together and we can use evidence that we have from various reactions to put together a table of a bunch of these sorts of reactions. So for instance, if we look at that silver nitrate reaction with copper that we talked about earlier, we see that it does react and we end up with copper nitrate and silver. If we took the opposite in terms of the ions and the metals, so if we took copper ions with silver metal and we tried to react them, we could stick them in a container, let them sit, nothing would happen. So we would show that as no reaction. So we can see of the reaction that happens, silver goes from +1 to neutral, so it's gained an electron, it is reduced, so copper is the reducing agent. Copper, on the other hand, goes from the metal to the +2 ion, so it is oxidized, and silver is the reducing agent. So we would say that copper is a stronger oxidizing agent than the silver in the second reaction because it doesn't happen. And likewise, silver is a stronger oxidizing, silver ions, I should say, are a stronger oxidizing agent than the copper ions are in the second reaction because the first reaction happens and the second one doesn't. So from reactions, we can figure out lists of things. So I'm giving you this list. We're not going through every reaction. We know that for oxidizing agents, silver is going to be the most of this particular group of 6, and sodium is going to be the least reactive. If we look at the reducing agents, their corresponding metals, it's going to be exactly the opposite. So we can put these together in a table, and we can see the strongest oxidizing agent is at the top, with both half reactions shown, right, with that reverse symbol. And the strongest reducing agent is down at the bottom on this side. So this was similar to our table of acids and bases where the strong acids were up on one side, the strong bases were down on the other side. So now we have the strong oxidizing agents up on one side, the strong reducing agents down on the other side. So we can look at a table like this and use what's called a redox spontaneity rule, which says if our oxidizing agent is higher than our reducing agent for any particular pair, you will have a spontaneous reaction. So using that silver and copper that we looked at a moment ago, silver, in the reaction that did happen, we had silver ions and copper metal. So the silver ions reacting with the copper metal. So our oxidizing agent was higher than our reducing agent. It was a spontaneous reaction. If you look at the second reaction, we had copper ions reacting with silver. Our oxidizing agent was lower than our reducing agent, so it was a non-spontaneous reaction. In general, we can say if you take a line and join the two things you're looking at, if you get a downhill line, as we read from left to right, think about if you put a ball at the top of that hill. It would spontaneously roll down. On the other hand, if we drew a line from the copper ions to the silver ions, if we put a ball on the left-hand side, it wouldn't spontaneously roll up to the silver. We would have to give it some sort of push. So it would be a non-spontaneous reaction. So we're going to use that spontaneity rule to look at a couple examples and decide whether or not they're spontaneous. And let's shrink this down a little bit so that we can see where we're at. So if we have tin metal in a solution of copper ions. So tin metal's right here. I didn't shrink down enough. I want to get them both on the same screen. So if we have tin metal in a solution of copper ions, so tin metal's on this side, and our copper ions are on this side. So for this question, let's just do a little highlighting. Right, we're connecting those two. So if we connect those two, we can see, yes, that's going to be spontaneous. And we can actually look at the complete equation. We can use our reaction that we had here, just as is. And the one where this is written as a product, we're going to have to flip around and make it a reactant. This particular one, we have 2 electrons, so they cancel out. It's just a matter of adding up our reactants and our products and canceling the electrons. Second example, we have silver metal in a solution of cobalt ions. Sorry about my word not cooperating. So silver metal, let's use a different color here, in a solution of cobalt ions. Take our uphill line and we can see, oh, wait a second, that one doesn't want to go on its own. We would say that one is non-spontaneous. So that is a very small table. There's only 6 substances in that table. You can actually find much larger tables, including the one that is in your chemistry data booklet. So if you take a look at your chemistry data booklet, we've got a table of selected standard electropotentials. What page is this on? Page 9 of your data booklet. And it's got quite a few more. And again, this is still selected substances, so it's not going to be everything. But we can see from this table we can do that same kind of thing. If the thing we're looking for is above, so if the 2 things we have, if our oxidizing agent is above our reducing agent, it's going to be spontaneous. So looking at our larger table, we can predict things for a lot more reactions. So nickel metal in a solution of zinc ions. So this one's a little more challenging. We've got to find nickel metal and we've got to find zinc ions. So here we have our nickel metal. And now we've got to find our zinc ions. So the numbers at the side we haven't talked about yet. We will talk about that later on. Zinc ions are right here. Well, I highlighted a little more than I wanted to, but you get the idea. So if we look at our zinc ions compared to our nickel metal, we are going uphill. So this one is also a non-spontaneous reaction. Chlorine gas bubbled through a solution of iodine ions. So up till now we've had a bunch that are metals, but this table also includes things that are non-metals. So you might have to look around for them a bit, but chlorine is a few places. So we've got to make sure we've got the right chlorine. So we've got chlorine, we've got another chlorine, right? Chlorine ions, chlorine gas. So the one we wanted in this question was chlorine gas. And it was bubbled through a solution of iodide ions. So there's our iodide ions. So we can see, oh, chlorine gas to iodide ions. This one is going to be spontaneous. Top reaction we're going to write just as it is, but the bottom reaction, remember to flip it around so that the sodium ions are, sorry, not sodium, iodide ions are on the reactant side and the iodine solid is on the product side. So let's write those into our example. So chlorine stays the way it is. Iodine reverses. When we look at the net reaction, again, 2 electrons are canceling 2 electrons, so we just need to write the reactants and the products. When we're looking at these, basically what's going on is there's a tug of war going on for these electrons, and if the stronger oxidizing agent has pulled the electrons away from the weaker oxidizing agent. We can also use that table to figure out what's the most likely reaction going to occur if we have a mixture of substances. And when we figure out the most likely reaction, it may or may not be a spontaneous reaction. So these questions often involve mixtures that have more than one thing in them, more than two things in them. So here we've got copper metal placed into an acidic potassium permanganate solution. So the solution says, well, we've got water, but it also says that when we have something like potassium permanganate, we can break it up into its separate ions, potassium ions and permanganate ions. So what we want to do in these sorts of questions where it says, what's the most likely reaction, is figure out, well, what is present. So copper metal is going to be a solid. Acidic tells us we've got hydrogen ions. Potassium permanganate solution tells us we have potassium ions, permanganate ions, and water. So start by looking at what's present. Once we know what is present, we can take that list and look at our table. So to find what's most likely to happen is we want to look at, well, okay, which reaction, half reactions, do we have the substances for? And generally, we start looking on this side for the highest possibility, because the most likely thing to react for our oxidizing agent is going to be higher up. So we had permanganate ions and we had hydrogen ions. So because it's in acidic solution, this one can happen, right? It's high up. So that's our potentially strongest oxidizing agent that's present. Now some of the other things we had there are also present, but we're really only concerned with the strongest one. Going back to what else we had present, we want to find our strongest reducing agent. So we're going to do exactly the opposite. We're going to start on the bottom. So we're looking for a reducing agent starting on the bottom, and we're looking for what we've got. So nothing, nothing, nothing. Keep moving up. Oh, there's the copper that we had. Now if we kept looking up, we would see there's some other things that we had. For instance, water. But copper's the one that's lowest down. So our strongest oxidizing agent and our strongest reducing agent are going to be the things most likely to react. If we get that downhill, it's going to be spontaneous. But if our strongest oxidizing agent is below, it's still our most likely reaction, it's just not going to be the spontaneous reaction. So in this particular case, our reduction reaction ends up being that permanganate reaction. We can write it straight out of our book. This is an acidic solution. We did that earlier and we weren't using the table. So now you see we've actually got a shortcut for those ones that are in the table anyways. The shortcut doesn't work if it's not in the table. So the reason we went through the earlier reactions where we actually had to figure out those things was sometimes we're not given them in a table. If we don't have them in a table, we might have to figure them out ourselves. So our reduction reaction, we flip that one around. This one doesn't match for our electrons. We have 5 electrons in that permanganate and acid half reaction, and only 2 electrons in our oxidation. So to make these ones match, we're going to have to multiply to get a common value. So we need to multiply the top one by 2 and the bottom one by 5, so we get 10 electrons in each. That way our electrons can cancel, we can write our overall reaction. So on this question, it did specifically say indicate whether the reaction was spontaneous, and we already said it's spontaneous. So when we write that overall reaction, we're going to write spontaneous above the arrow. Second example, we've got a lead strip placed in a tin chloride solution. So what's present? Well, lead strip is solid lead. Tin 2 chloride tells us we have tin ions, chloride ions, and it's in solution, so we've got water. So again, we go over to that table. So we've got lead as a solid and tin 2 chloride. So tin's a little tricky because we've got tin 2 right here, but we also have tin 2 right here. So it's an oxidizing agent and a reducing agent. So it could show up in our equation. We had chloride and water. We have, oh, not that one because it's got hydroxide, which we don't have. We have chloride here. I know I'm getting overly highlighted on my diagram. And what else did we have? We had lead. Where is that lead? Right there, lead. So looking at our strongest oxidizing agent, it looks like it's going to be the tin 2. Our strongest reducing agent is going to be the lead. So it's going to be these two equations. Oxidizing agent, we write the same way it is because it's already a reactant. Reducing agent, the thing we want, needs to be a reactant, so we got to take this one and flip it around and put lead as a reactant. So keeping our tin one the way it was, switching our lead one around. Right, so our table is a reduction table. The one we keep is the reduction. The one we flip around is the oxidation. Now, if we look back to those two on our table, tin was below the lead, so this one's uphill. It's only a tiny bit uphill, but it's still uphill, so it's not spontaneous. So when we write that overall reaction, 2 electrons cancel 2 electrons, no multiplication needed, we see we've got a non-spontaneous one. I suggest you pause the video and try the next one on your own before scrolling up to look at how we get the answer. So on this one again, we've got a big mixture of things. Potassium dichromate solution added to acidic iron 2 nitrate solution. So again, look for the strongest. Potassium dichromate is actually going to be pretty high up because there's our dichromate and it's in acidic solution, and we know this one's acidic. So that one's pretty high up. So that will be our reduction reaction. Nothing we have there is higher. Acidic iron 2 nitrate. So could possibly have potassium ions. Let's take a look. Acidic iron 2 nitrate. So be careful again when we're looking for these. So what do we have? Okay, I know what's in here. There's my iron 2. Iron 2 is another one that, like the tin, shows up more than once. So we do have iron 2, there it is off the screen, down a little lower, but that's not going to be the reaction because it's much lower than the dichromate reaction. But we don't have anything on our reduction side that's a stronger reducing agent than the Fe plus 2. So that one we had to flip around, and there was only 1 electron versus the 6 in the other reaction, so we need to multiply that one by 6 and cancel our electrons, and that one will be spontaneous because the reduction was above the oxidation. Again, I recommend you try the next one. I'm not going to go through all the details, I'm just going to show you the answers to this one. So our highest possible one on the reduction side was the iodine crystals, right, the solid iodine. The lowest one on the oxidation was those sulfite in a basic solution. So we have to have both things present in order to pull them off of our table, but we do, so we can use that one. So that one, when we compare them, the reduction is above the oxidation. It ends up being a spontaneous reaction. And again, this one we had 2 electrons, cancels our 2 electrons, so no multiplication required. The last kind of semi-topic in this section is looking at disproportionation. There are some species that can be both oxidized and reduced, and that tin that I mentioned earlier is one of them. So if you look, tin 2 ions can gain 2 electrons to become tin metal. But because tin is multivalent, it also forms another possible charge. We can end up with tin 4 by losing another 2 electrons. So the net reaction on that one, well, we start out with 2 tin ions, 2 tin 2 ions, and we end up with both tin metal and tin 4 ions. But if you look on our table, the question about whether it's spontaneous, well, there's the tin ions and there's the tin ions. Uphill reaction. So this one's not spontaneous. And we'll call that one a wrap.